All right. Good morning and welcome. Today, we will continue our discussion on growth and decay problems. Let me just check if my stream is working here. Everything seems good. All right. Okay, 1 second. There we go. Okay. So let's recap what we have done. Get my cable here. Come on. There we go. Cable is stuck. Okay, good. So let's just recap what we have done so far with growth and decay problems. Because it's good to have a big picture of what we've done, where our current level of complexity is, what we are going to do next, and why, and so how is it different, how is it the same, those kinds of issues. So if you remember, we started with our basic exponential, whoopsie, there's an I missing in there, growth. Then so here our basic exponential growth says that the growth rate is proportional to the population size. Then we had a look at radioactive decay problems, where we saw that the differential equation looked exactly the same, except we were going to go down. K was negative in this case. K is positive in this case. Positive growth constant. K negative decay constant. But the rate of change was still proportional to the amount. Population size, amount left. It had the same look and therefore the same solution process and the same function that we had to analyze to answer our word problems. Then we said, okay, well, let's look at exponential growth, but understand that there are space limitations involved. That if I put fruit flies in a jar, eventually they're going to run out of space. And that affects my growth rate. So we looked at a different version that said that the growth rate is proportional to how far away the population is from that capacity. That we'll call n, for example. So we still have a growth constant here, but now we're looking at the growth being proportional to something else. And we saw that in comparison to the basic exponential growth, we now had a situation where we had a capacity line, and I start with my initial population and it's going towards that capacity, but it'll never get there. The closer it gets, the slower it grows. So let's put a pin in the pros and cons of 1 and 3, because it seems like together they are the ideal situation. Initially, the things that grow, whatever the specific topic is, bacteria growth, fruit flies, goats in a field, whatever that may be, they don't have any care for capacity in the beginning. They're so far away from it. So the exponential growth would be very similar to basic exponential growth. But as we get closer, then this portion of the basic exponential growth becomes unreasonable, and the capacity aspect, that it slows down the closer I get to the capacity, becomes more realistic. So a combination of these seem to be the direction to go in. But unfortunately, that is a big jump in complexity. So we just want to look at some variations of this level of complexity. First, to see how many different situations we can really cover with these fairly basic proportionality differential equations. The next one I want to look at is Newton's law of cooling. Cooling? Can I write cooling? Oh, come on. Cooling. There we go. So let's see what that says. Let's just write it over here. Newton's law of cooling says if I have like a cup of coffee that's really hot and I want to leave it out to cool. So first we're going to say, okay, let Y represent the temperature of the object at time T. Now, in the case of a hot cup of coffee, that temperature, if I leave it out, is going to decrease. So we have a decaying situation here. The temperature, if you will, is decaying. But what Newton observed was that the rate of change was proportional to the difference between the temperature of the object and the temperature of the surroundings. So the room temperature in the case of leaving out a cup of coffee. So let's, for simplicity, make that N for no reason whatsoever. So again, I have a similar differential equation that there's my proportionality constant. There's difference between the temperature and the room temperature. So in the case of a hot cup of coffee, this is often room temperature or a temperature that is known beforehand. So you see how it's very similar to the exponential growth with capacity. Very similar in appearance. But now I'm going to have a sort of a decaying effect. So it's not going to be identical, but very similar. All right. So let's just have a look at this. So let's suppose, let's just take an example. Hot cup of coffee. Left outside. Then my Y is going to be larger than my room temperature. So the difference between the temperature of the coffee and the surrounding temperature, Y is going to be bigger. The coffee is much hotter. So this is going to be positive. So the temperature, however, is going to be decreasing. So the rate of change of Y is going to be negative. So in order for this differential equation to make sense, I'm going to have again a negative K, and that's sort of like the decaying concept. The temperature is decreasing. I have something that is decreasing over time. Okay, no, we don't call it the decay constant. It's just the the proportionality constant that comes from that's associated with the coffee. It's a property of the coffee and the volume of coffee and the surface area, and all those things just merged into one. So let's have a look at what this would go like, the solution, in a specific question. Now, if you look online, there might be different versions of this differential equation. Some people like to keep k constant, and then we have to manually put a negative there in front. But we didn't do that for the radioactive decay, so it seems a little silly to do that here. We just have to understand that in some cases, for this to balance, I'm going to have a negative constant. Radioactive decay had a decay constant, where population growth had a growth constant. All right. So let's have a look at number 34 here. Let's do it over there. 1434. You are cooling a turkey that was taken out of the oven with an internal temperature of 165 degrees. After 10 minutes of resting the turkey in a 70-degree apartment, the temperature has reached 155. What's the temperature of the turkey 20 minutes after taking it out of the oven? All right, so we have our surrounding, our ambient temperature of 70 degrees, and our initial temperature is 165. Time seems to be in minutes. So let's say here, Y represents the temperature of the turkey at time t, and that would be in minutes. Then my rate of change, according to Newton's law of cooling, is going to be the temperature of the turkey minus the 70 degrees surrounding temperature. And my initial temperature was 165. So I find it's best with these to just solve the differential equations as they come up in the questions rather than worrying about a general solution and a formula. It doesn't really serve our purposes for these kinds of questions, so why stretch the time when there's very little need for that in this case? Okay. So now we have a differential equation. It's not more or less complicated than the previous capacity growth one. So let's do it. So I want to separate the variables. So my bracket is going to have to go to the other side. I can only separate the variables with multiplication and division. Can't really separate this y and the 70. Then I integrate both sides. Then this left side is a substitution, but it's so simple I can guess and check my way to it. I know to be more accurate here I need absolute values, perhaps sometimes, to not even worry about it, but because in the cooling situation my temperature is always greater, we are just going to keep it as simple as possible to not get caught up in technicalities that eventually fix themselves. So if you know a little more, I understand there should be absolute values here. I'm trying to not make it look more intimidating than it needs to be. And I group my integration constants at the end here. So then y minus 70 is e to the kt plus c. And just like always, we will rewrite the integration constant to a more convenient one. And then I might as well solve for y now. I get 70 plus m e to the kt. There you can put the 70 at the back. It doesn't really matter. Then I'll use the fact that at 0 I had 165-degree turkey. So 165 for y gives me 70 plus my integration constant e to the k times 0, which is 1. And this gives me my m as 165 minus 70. I'll just put it in the chat so you have something to look at. And it is, of course, 190, not 195, just 95. So where are we now? So we have our function of time, which is 70 plus 95 e to the kt. So it's you remember that regardless if the growth constant here is a decay constant or positive or negative, e to the something is always going to be positive. But I'm really just having a scaled amount, exponentially scaled amount, above 70. And that is eventually going to get smaller, but I'm always going to be above 70. So let's have a look. I don't know my quote-unquote decay constant. Let's just see it at the top here. But they do tell me something. They tell me that after 10 minutes, the temperature has reached 155. So let's write that here. After 10 minutes, so that means t is 10. We have y equal to 155. So we can plug that in. So at 155 for y, everything else is the same. K is what I'm looking for, and 10 for t. So 95 e to the 10k is 155 minus 70. So that'll be 85. So e to the 10k is 85 over 95. 10k, and I'm not skipping any steps just in case you don't see the similarities between this and what we've done before. I then take the log of 85 over 95, which you could simplify first or not, doesn't matter. That goes in the log. And k is log of 85 over 95 over 10. Let's see what that is. Let us see. We'll ask MathBot for some help. Oopsie. And as I suspected, it is negative 0.01112, let's say, if I go 4 significant digits. So I have my quote-unquote decay constant, the proportionality constant associated with this turkey. And it's not going to be exactly the same for every turkey. It depends on how big the turkey is. It depends on a whole bunch of things. I do now have all that I need in my function. So I can answer their follow-up question. What is the temperature of the turkey 20 minutes after taking it out of the oven? And we can make our own questions as well. So after 20 minutes, we simply use the function and plug in 20 for t. 70 plus 95 e to the negative, not negative. Well, you can put the k value in, but because it's a repeating decimal, not repeating, non-terminating decimal number, it might be cleaner to just leave it like that. Though I do understand that the situation has a negative exponential portion to it, which means again I'm going to have the situation over time where here is my 70, my room temperature. It starts at 165 up here, and I'm going to exponentially go down towards this as my horizontal asymptote, because k, the exponent, is negative. So it is modeling the appropriate situation. So now I want to calculate that, and when I have a future calculation, I don't want to use the rounded number. Use as many digits as you can, or use the original log over 10 version. Let's see what it is exactly. 70 plus 95 times e to the stuff, 20 times the log. I want to be as accurate as possible, so I'll use the log 85 over 95 version, and that was divided by 10. Like so. And I get an answer of 146.05. So after 20 minutes, it'll be approximately 146 degrees. And then we can decide things like, well, what is a temperature where food is safe to eat? At what temperature is food safe in the terms of it not burning my mouth? Not in terms of killing all the bacteria. I'm just trying to do a quick Google search here. What is it? When is food not going to burn my mouth? At what temperature does food not burn your mouth? Let's see what Google says. I don't want to show it on the screen, but let's see here. It's a random. How hard is this to find? I guess it depends if it's liquid and what kind of food it is. You could say, if I leave out the turkey, how long before it's going to be a little bit too cold to eat? Let's suppose at 130 degrees, it's not enjoyable anymore. So we could say, I want to give my guests a time window, and when it's too cold, when it's cooled down too much, then I need to be done with my whole meal. So when will the temperature be, let's say 130? That's going to be how long I have for this meal. But it's a simple calculation for us. We want to have a y value of 130. We then want to solve for time. And I know my K, right? I write the K, but I remember that I know it whenever I need to. So I'll just go a little faster here because I'm running out of space. We could say, well, 130 minus 70, that is 60. So 60 over 95. So KT will be natural log of 60 over 95. So T is what I'm trying to solve here. Log of 60 over 95 over K. Let's see what we get. Remember to not use a K value that is rounded too much or at all. So log of 60 over 95 divided by, now we could use our most accurate K, which is up there on the screen, log of 85 over 95. I could have simplified that, but that's too late for that now. Like so. And what do we get? 41-ish minutes, 0.32. So that'll be in minutes. So if I take my turkey out of the oven, 41 or so minutes approximately later, it's going to start getting a little cold, and my guests might not enjoy it. Now, they might not be able to eat it right away either, something in the middle, but at least I have an idea of my time window. So interesting things like that can be done, especially if we read other questions. Like there was one about coffee. So here, according to experienced baristas, the optimal temperature to serve coffee is between 155 and 175. Suppose coffee is poured at a temperature of 200, which will burn my mouth, and after 2 minutes in a 70-degree room, it is cooled to 180. That extra information gives me an idea, or gives me a way to find the cooling constant, let's call it, for this specific situation. When is the coffee first cool enough to serve? When is the coffee too cold to serve? They need to know these things. Otherwise, the customers are going to be unhappy. So let's have a look at this one, which is number 136. I don't need to split this over 2 pages here. It's still just Newton's law of cooling. So it's very similar, but perhaps something that we can identify with as being quite practically relevant. So 1436. So we're going to, of course, have our function variable represent the temperature at time t, not 6, t. Now, how am I measuring t? Let's just have a look here. Optimal temperature between these two. Okay, sure, that's going to come up later. Coffee is poured after 2 minutes. So let's count in minutes. Then my coffee is going to cool at a rate that is proportional to the difference between the coffee temperature and the room temperature, which is 70. What is the initial temperature? They say it is 200. So 200 degrees, the initial coffee temperature. Now, I go through the motions and solve this differential equation. It is identical to the previous one, which is perfect practice. Separate the variables, then antiderivatives, which are fairly straightforward by now, I would hope. Kt plus integration constant. Y minus 70 is therefore e to the kt plus c, rewritten to a nicer integration constant. I have my general solution or a version of it, and then initially I have a temperature of 200. So 200 for y, everything else is the same, and t is now 0, making this a 1. And so m is the difference, which is going to be 130. So my function of the coffee temperature changing over time is 70 plus 130 e to the kt. Now I don't know k yet. I need more information, but that is certainly my function that I will use. So this is why they tell me that after 2 minutes, it's cooled to 180 degrees. So we also know and can extract the property of the coffee in terms of how fast it cools, that at 2 minutes, I have the coffee at 180 degrees. So that means plug in 180 for y into the function, e to the k times 2. So 130 e to the, I'll write 2k, is therefore 180 minus 70, which is 110. So e to the 2k is 110 over 130. And so 2k is the natural log of that. And k is then the natural log over 2. Whoopsie, that was an unfortunate line there. I want to cut into the 2. And I can calculate it just to make sure I can. But I certainly don't want a rounded number featuring and risking in future calculations that I make a mistake. MathBot says nothing. MathBot says nothing. Why do you say nothing, MathBot? Be faster. Negative 0.08353. All right. Now I know my function that will go in there whenever I need it to. Let's see what they say. They now want to know, what is my window here? When is the coffee first cool enough to serve? So when do I get a target of 175? When is it too cold to serve? According to this, after 155 degrees. So 175 to 155 is my time window. So a temperature of 175 is going to happen when? Well, when I plug it into y, what was my function? Up here, 70 plus 130 e to the kt, and I solve for time. So let's do that a little bit faster. E to the kt, isolate that first, so it's going to be 175 minus 70, so it's going to be 105 over 130. So therefore kt is the natural log of that, and t is therefore natural log 105 over 130 over k. So let's just write these out before we solve them. I don't want to ruin the surprise. I also want to know when the temperature is 155. That's the end of my window. So it's going to be exactly the same with a 155 for y, but follow the same look, the same pattern, and everything. You can verify that it's going to be the natural log of 85 85. Didn't we do 85 before? It seems so familiar. I guess that was a different question. 155 minus 70 is 85. And then I divide by 130. Same argument as before. The pattern is always the same in these two questions. So let's see. When can I serve it first? So when is it 175 degrees? So I have the natural log, and I'm typing it in, so feel free to follow with me on your own calculator. I'm going to divide by k, but instead of the rounded version, I am using my k up here. Where am I now? Log for the numerator. Then I'm dividing by k, and k itself has a log function in it, 110 over 130, and then that k is divided by, or that numerator in k is divided by 2. Let's see what we get here. We get 2.56, let's say, and that's going to be minutes. And for the end of the time window, I'm not sure if I could just do it this way. Recycle a previous entry for MathBot. I'll give it a shot. It does work. Okay, good. Just changing the 105 to an 85 as per our calculations. I get 5.09 minutes. So that means I can serve the coffee from, or let's say after 2.5 minutes, approximately 2.5 minutes, but before 5 minutes after it was created. Approximately, of course. Approximately. My P's are always so weird. Whatever. So we get the idea. So very practically relevant question, I would say, that to keep the customers happy, they could test beforehand what do customers like in terms of the temperature of their coffee on average. That means we need to be how fast before we could serve it, and when is it too slow, and all those things are very important questions that a basic differential equation solves for us without most people actually realizing it. So we will end this discussion here. We do have a fifth one as well, just to see what else can be done here without drastically changing the complexity, and then ultimately can we be a little fancier with our exponential growth, and what does that look like in terms of mathematical complexity, and how much do we gain in terms of practical accuracy. But until next time for that.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.